Welcome to this explainer on equipment selection and X-protection methods. Today, we're jumping straight into one of the most counterintuitive safety concepts in hazardous area engineering. When we think about working in explosive atmospheres, like offshore drilling rigs, chemical plants, or LNG facilities, our very first instinct is usually absolute prevention, right? We want to stop any spark, at all costs, to prevent an explosion. But today, we're looking at a fundamentally different philosophy. Yeah, rather than trying to prevent an explosion, the Flameproof Enclosure method, which the industry calls XD, relies entirely on surviving it. I know, it sounds crazy, but this protection method doesn't even try to stop an explosion from happening inside the electrical equipment. It literally just lets it happen. But it happens inside a box built strong enough to survive the blast, and engineered so incredibly tight that the flame never ever gets out to the surrounding hazardous area. Honestly, it acts a lot like a heavily engineered pressure cooker. Section 1, the flame path mechanism. Let's look at how containing this blast actually works in practice. So according to IEC standards, specifically IEC 6007914, this protection method is really all about brute force mechanical containment mixed with highly precise venting. Imagine a flammable gas mix seeps into an electrical motor or a junction box, and a spark ignites it. Boom! The enclosure must withstand that massive structural shock. But all that rapidly expanding explosive pressure, it has to go somewhere. It escapes through the joints of the enclosure, which are machined to incredibly tight tolerances. And this brilliantly illustrates the life cycle of that blast. The hot gas is squeezed through a tightly toleranced gap, which we call the flame path. This path actually forces the escaping gas to travel a very specific distance through a super narrow gap, effectively stripping it of its thermal energy. By the time it reaches the outside explosive atmosphere, it's been cooled way below the ignition temperature, so it's completely harmless once it hits the open air. Section 2, clearance by gas group, giving the gas room to cool. Now, the minimum distance between that escaping flame path and any solid obstacle scales directly with the volatility of the gas group. As we can see from the standards, more easily ignited gases just need more clearance for the escaping gas to cool down safely. For Group 2A gases, like propane, you need at least 10 millimeters of clearance. For Group 2B, like ethylene, that jumps up to 30 millimeters. And for your hydrogen-grade risks, which fall under Group IC, you need a full 40 millimeters of breathing room. The documentation is incredibly strict on this, and for good reason. If you place a wall, a pipe, a weather guard, or even a simple mounting bracket too close to that flange, the escaping gas won't have the space it needs to cool properly. The pressure piles up, the heat gets trapped, and the hot gas hits the obstacle and deflects directly into the explosive atmosphere. So, by ignoring those clearance distances, you are literally turning a safe, engineered vent into a catastrophic ignition source. Section 3. Never paint a flange. Protecting the gap. Now, while corrosion protection is absolutely necessary, especially in those heavy marine environments like offshore platforms, applying paint or hardening substances to the flange is a huge mistake. It changes the engineered gap tolerance and traps the heat. You can use non-setting grease or certain anti-corrosive agents, and actually, in some specific lower-risk gas groups, a single layer of non-hardening tape is allowed on the outside of the joint. But you must never paint the flameproof joint itself, and you can never add a gasket unless the original manufacturer's certification specifically calls for one. Section 4. Test your XD knowledge. Let's look at a practical maintenance scenario. Okay, put yourself in the shoes of an offshore technician trying to do the right thing by protecting equipment from a harsh marine environment. You see a heavily corroded XD motor housing. To protect it from the salt air and stop further degradation, you clean it up and repaint the entire housing, including brushing paint right over the flange joint. So, what do you think? Is this the correct safety procedure? The answer is absolutely incorrect. Painting the flange actually invalidates the entire safety certification, because the flame path can no longer guarantee the gas will cool down before escaping. Even a tiny, thin layer of paint alters the micromillimeters of clearance that the flame path relies on. Plus, paint can harden, and it can actually mask dangerous underlying corrosion that is quietly eating away at the joint's integrity over time. Non-setting grease is the only approved method for protecting that specific joint, even if the rest of the housing can be repainted. So we've explored how these enclosures survive an internal explosion, how flange clearances must scale with the volatility of the gas group, and how a seemingly innocent maintenance mistake, like painting a flange, can quietly invalidate an entire safety certification. But what if a totally different method didn't try to contain anything at all? Section 5. Next, Increased safety. XC protection. In our next explainer, we're going to explore a completely different strategy, one built entirely around good engineering practice instead of brute force containment. Until then, keep those flame pads clean, respect your clearances, and stay safe. But I want to leave you with this one question to think about. How exactly do you design electrical equipment with such perfect, high-quality insulation and spacing that it never produces a spark or a hot surface in the first place?